So this is just to let you know that I have started the recording, and it will be great if I can request that all participants mute themselves. It will really help with the sound during the presentation. If you've got a question, you're welcome to put up your hand. The speaker said that it is fine with questions during the presentation. So if you've got any questions, please put up your hand, and I will ask your question to the presenter.
Thank you, Rita, for doing that. I appreciate it.
Perfect. So we've got 1 minute to go, then we can start.
Okay, shall we? Three of us?
I'm good. I'm ready if
Okay.
it seems this.
Okay, so let us start, Rita. You have also recorded the session. So very good day, very good evening, very good evening to everyone who's joined this webinar, IOHA webinar on additive manufacturing. I would like just to mention that this session is recorded for everybody's knowledge. And today, this evening, for me, I'm dialing in from Malaysia. My name is Nur Hazlina. You can call me Lina. I'm currently the immediate past president of IOHA. Was also the past president of Malaysian Industrial Hygiene Associations and currently working as the head of strategy and performance of Petronas HSC. Yeah. Dialing in from Kuala Lumpur. So I'm on behalf of Maharshi, the IOHA president, I'm pleased to invite Srinivas to be with us tonight. Let me just highlight some of his experience. Yes, Srinivas. With 18 years experience in EHS risk management of new technologies, this is definitely a unique experience, especially dealing with new technologies that we are pleased to have you around. And currently you are with SC Johnson as the EHS director, and you have spent quite a bit of experience, quite a lot of experience actually with GE. And that is also where you look at product stewardship in additive business, where you have actually looked into the development and execution of risk management for 3D printing. And you're also very passionate in volunteer work. I've seen in your CVs that you've worked as, you serve as the board of directors of IHA and also the American Board of Industrial Hygiene. So without taking much time, on behalf of IOHA, I would like to welcome you, and I would like to welcome all the participants for today's webinar. Do type your questions or your feedback, your opinions in that chat box. And if we need be, Rita will also be assisting Srinivas to pick up those questions as necessary, because sometimes it may be too late to wait to ask or feedback relating to slide number 3 at the end of the session. Yeah. So if this approach is also fine with you, we will adopt that message as well. All right. So with that, I hand it over to Srinivas.
Thank you, Lina. And Rita, appreciate the opportunity at this point to share some of the key learnings I've had as a business unit EHS leader for GE focused on metal and polymer additive manufacturing. As Lina mentioned, I had I'd say the pleasure and the challenge of building a risk management strategy for additive manufacturing for GE from ground up. It was an inorganically acquired business. I'd seen this technology with 6 years in R&D in upstate New York, and that opened the eyes of when I think of future of work, the core pillar technologies that enable this. Additive is one that realizes the scope and the creativity that as humans we have and turns that into physical objects, right? So with that implication and with what it could mean for us, understanding that from a overall EHS and you could narrow it down to an industrial hygiene OH perspective, I want to share some key lessons learned working through the business, the technology landscape, what it sees. So looking forward to a more an interactive conversation. So feel free to raise your hands. I lean on the Lina and Rita to raise the questions so I can absolutely address it. And good evening and good morning and good afternoon to folks who are joining in. Appreciate this at all. So let's get into it. So just from a content perspective, I do have a couple of questions to help set the stage as I get in the conversation. Key part when we think about additive, as I talked about Industry Revolution 4.0, it's one technology that you guys have heard about, which anchors the conversation on realizing the digital to physical. But it's one, in my experience, has implications across multiple sectors, right? So a couple that I've highlighted here, coming from aerospace, it has one of the stronger proof points with industrialized metal parts. I'm sure you have all seen versions of consumer level 3D printers that's easily accessible, primarily on the polymer side. But you're also looking at key maturations in healthcare segment, whether it be the first titanium chest implant that went in 3 years back to the 100,000 titanium hip implant, both in human and animals. If you have a pet or a dog, these are very commonly custom-made implants that are put in. To right now, when you think about what the kids need, my son is going through his phase as a 12-year-old who requires dental work, the 14 billion Invisalign unit that's made every year by the company that's actually put into the marketplace, to something that's probably from a lifestyle standpoint, you wouldn't be thinking about. If you're a golfer or a runner like myself, Adidas actually has a midsole shoe that's completely 3D printed, the bottom part that I've highlighted here. Really talks about one technology that has implications. The poster child for when I was part of GE was the fuel nozzle, truly where it was a consolidation. This is in the hot section of the aircraft turbine, which disperses the nozzle into the turbine, right? 20 to 1 part consolidation that you can see, right? Single alloy manufactured using additive manufacturing. The key part as we think about, yes, penetration across multiple sectors, as we went through COVID, one of the key things we all heard about from our supply chain leaders was around, hey, the challenges with supply chain resiliency. With that tailwind where we were trying to get through and see, can we source products where we need to be, there's a clear, I'd say, conversation on a higher level about what does onshoring means. And with those tailwinds, we'd expect more of additive manufacturing to take place because it has capability to do in situ manufacturing, which is at point of use, whether it be it in dental segments that I highlighted. And you see a maturation with those specific sectors as you look at the graph on the right. Medical and aerospace with the application space ripe for specific high temperature alloys, which are both in this case FDA and FAA approved, to where other sectors are growing. I would highlight here with construction, which you see potentially as a laggard, there is a significant growth rate with focus on additive manufacturing being used for printing houses, right? Taking the turnaround time, or in this case, you could argue the cycle time from few months to couple of days where they're able to actually realize a completely finished product. With this, you'd expect that more 86% doubling over the next 5 years, which is quite exciting to see and gives us as EHS professionals and OH professionals, right, being able to anticipate in the segment that you are in and being able to understand what the implications of this technology means. The part I highlighted, the fuel nozzle, is a phenomenal example, what I'd call a poster child. Additive's value proposition is not truly in creating widgets, right? If you want to make a block of material, that's not where the value for additive exists. Truly where I've seen additive creating value for an enterprise is where you are able to realize complex shape that cannot be manufactured. As you look on the graph, being able to realize that through part consolidation, unleashing both reduction in design cycle time, as well as the efficiency and reliability of parts or components that you're creating. So one-to-one replacement really, in few instances, yields value, but consolidation is where you see significant improvement in efficiency and reliability. Aerospace example would be a clean sheet design of Catalyst aircraft, which was specifically the engine. This was significantly a third of that entire engine was built with additively manufactured parts that were not the same from prior, but were entirely designed for additive application. And it's, if you look at Deloitte, it's talk about when you think of the number of steps that go in, when we think about sustainability, right? You're talking about not only your scope 1, scope 2, the scope 3 being the largest part where you're sourcing your materials from multiple suppliers. Additive has inherent capabilities on shrinking the supply chain, requiring fewer assembly steps, and making sure when you think about transport density, where the part needs to move, just the digital file needs to be aligned and sent to the right space and you could execute your job, right? So both from a turnaround time, you have phenomenal capabilities when it comes to this technology. So jumping in, just to kind of expand now, these numbers are notional in nature. When I first created this as part of the additive business unit, and I see the codec is not working. Let me see if I can go back. There you go. It kind of highlights how additive applications are actually working. The energy usage and cost, right? Now, this completely depends on the specific part application that you're actually putting in place. The comparison of subtracted to additive, as you can see on the slide, single by single layer of either polymer, metal, or ceramic material being laid on, and then using energy. Now, energy could be in multiple forms, whether it be in an electron beam, laser, photocuring UV light, ends up creating the part in 3 dimensions as the plate lowers. So primary usage, you're not subtracting, taking away using a lathe or a CNC machine, a block of material and converting into part. You're just focusedly building the part. And there are a couple of key material spaces that we'll highlight and touch upon today. One, when I think about mature technologies, metals being primarily that is being industrialized. In polymer, there's definitely quite a few of custom manufacturing solutions. Take it from your iPhone case to a lockout device that we had seen built out specifically that we couldn't produce outside or procure it, to polymers that is now more and more being used in things like whether be it washers, dryers, components that can enable so your inventory is significantly low. Now, knowing we have a good bit of hour or so to cover, and there's a good bit of content in primarily metals and polymers domain. Question for the audience, what would be of more interest to you? Would you want to hear more about the metals additive manufacturing risk profile or polymer? Knowing there's a good bit of content I need to cover, it gives me a space for how much time I want to spend on one focused or maybe both. So open to some feedback from the audience at this point. And please chime in, type your responses in the chat box so I can monitor and then accordingly kind of jump into the right section.
Okay, metals, let's feedback about metals. Some mentioned both, polymer.
Okay. Both. Got it. I'll give a minute for others to type in. Hey, Paul, Michael, glad to see you guys join. All right, so we are kind of seeing more of a theme for both. So I'll probably pick up my pace. That way we can get through the conversation, and feel free to raise your hand. That way we can answer any questions. So I'll jump in with metals, right? So one of the, I'd say from an industrial manufacturing standpoint, the risk landscape is more diverse. So with any technology, there's quite a few of acronyms. This kind of highlights what I'd say the ISO aligned primary 7, the highlighted boxes that you have seen as the technology modalities that are out there that talk to about additive manufacturing, both risk profile and how the material use is currently in place. So for polymers, the primary 3, that'll be the second section I'll touch upon: material extrusion, material jetting, and vat polymerization. In the metal space, powder bed fusion, DED or direct energy deposition, and then one that's growing and has quite a big capability when it comes to high volume manufacturing is binder jetting. So we'll touch upon those 3. And it gives you a scale for when you think about where the printers have evolved. Some you may have seen, like the desktop printer by MakerBot on the far the left right here. to what I'd say in the scale, full scale or freeform additive printers that can pretty much house a human. The largest format printers that I've seen for metal, this is one example of it. It's the same size as a shipping container, but serial production machines are even bigger than this, right? So the scale of the equipment and inherently safe designs enable the technology to be used robustly, and we'll touch upon both what are those controls that make the technology safe. And price points, when I think about literature, quite a bit of that has been focused on polymer, primarily because of low cost of capital that's needed. But there's more work being done, specifically coming out of Sweden and Italy, that's quite exciting to see around focus on occupational health hygiene issues when it comes to metal additive manufacturing. Just to anchor our conversation, when we think about EHS risk management, this is one technology where it's important for us to think about both not just the process, which we tend to focus on, and the materials. Both of those two elements actually have a significant implication when it comes to deployment of metal additive manufacturing as it impacts the infrastructure need, right? So this is the building that you house in, whether be it a brownfield or a greenfield site that you're trying to build up to bring this technology in. In small scale, you can get away with it, but if it's going to be industrialized, that is full scale production, or even low rate production that warrants you to have that anticipation of risk and have the right conversation with your stakeholders up front. So IMP, right? So important to know your IMP, which is infrastructure, material, and process. So we'll start with process and work our way backwards to what those implications mean when it comes to infrastructure needs. And we'll cover the controls for each technology space. So getting into metals, the most ubiquitous or commonly used technology when it comes to metal additive manufacturing is direct metal laser sintering and electron beam. Effectively, in this case, as you saw the prior slide, a platen, which is effectively a build plate where you apply powder layer by layer, and use of either, in this case, a laser or an electron beam that supplies energy and then effectively sinters the metal powder in place. Now, this allows the part formation in 3 dimensions. The plate lowers, and you will have the part creation actually happening within, enclosed with the powder around it. The difference between the two technologies, between DMLM and EBM, DMLM is actually done with inert gas. So I would ask you to think about effectively like doing welding, right? Layer by layer, if you have ever welded, put a bead on, but you are doing that in an inert environment. So there are fume emissions that come out. The inert gas is actually recirculated to make sure you're capturing and reusing that from a utility perspective. And if you think about the fire triangle, right? So you have metal powder, which depending on the size fraction can be combustible. The fuel aspect of it, oxygen, and the energy source, right? The control here from a risk standpoint is actually ensuring your oxygen is completely devoid, right? So it's absent in the environment the work is actually happening because the energy is coming from either laser or EBM. So the risk mitigation primarily by inerting is an approach that makes this technology safe from an execution perspective. Laser aside, and we'll get into the controls, the gas phase that actually circulates inert gas actually has onboard filtration systems to ensure the welding emissions that we typically have studied in occupational hygiene is captured. Fumes do tend to be more reactive in nature, and I'll touch upon the why in the subsequent slides. Now, if you think from DMLM going to electron beam, technology that is highly used in medical applications, the implant devices I talked about, actually uses a high voltage electron beam, but the work is actually performed in a vacuum system, right? So it's completely brought down to 0 bar, making sure as these units, I see some peers joining from Sweden, Arcam is actually based out of there. And that allows this technology to, again, when you think about the fire triangle, take away the oxygen element, right? The air aspect of it, and being able to make sure we can perform and build the part. And this is both important from a quality of the part being created to minimize oxidation risk. So those are two versions of key technology that's quite popular. You're thinking about companies like SLN, GE Additive, Desktop Metal. Well, Desktop is on the binder jetting space that are actually bringing this technology in the marketplace at this point in time. Let's kind of talk about binder jetting. One of the benefits and the trade-offs when it comes to powder bed fusion versus binder jetting. In this case, binder jetting, I'd like you to think about more like effectively baking a cake, right? So here you do have screen printing technology being used where the powder bed is supplied and sprayed with fine nozzles, a polymeric or organic or water-based binder that's sprayed in the pattern of which you want to create the part. As the head rolls over, it glues and creates a green part, which is then subsequently cleared in the return step using curing light. The subsequent motion of this, the build plate descends, and the green part is bonded as the platen comes down. If you can imagine something that you're making with like a sandcastle, it is very fragile in nature. The couple of key steps that are required to sinter it and make into a full densified part is you bring it subsequently to a curing and a sintering furnace, curing to drive off the organic binders or water-based binders that you're using to densify, and then final densification is usually with sintering, right? So you have more than one set of process steps that need to happen. Last but not least, depending on the porosity, if you need densified part infiltration, which is you may be using materials to actually seal micro openings. Those are very common examples of what you would see binder jet. I briefly talked about the benefits and the trade-off earlier. Binder jet is one technology in metal additive manufacturing that is capable of high volume production. Think automotive application spaces where you can create the same part with reliable and the specs that you want. And this technology is maturing quickly and has the ability to kind of scale full-scale deployment. The last but not least, direct energy deposition. Truly, I'd say if I simply put it, it's welding in a even larger box scape, right? So you both have a version where you're working with metal powders, which are pushed through a jet with actuated nozzles, or it could be a wire, primarily in repair application spaces where you may be doing a high temperature component and you want to do field repairs, that's capable of it. There are some pretty cool applications of creating larger aerospace parts, specifically in applications like SpaceX is thinking about. But feedstock material varies. Just from a design perspective, you can see the operator is out of the weld pool envelope, right? But you could see, as you see in the size and scale, these are massive systems that are put in, capable of achieving deposition rates that's significantly higher than when you think of material, whether it be binder jet or for that matter, powder bed fusion systems. Those are few elements that I'd say make this more suitable, primarily for large part and repair technologies that is out there. I'll take a pause. Maybe I'll open the floor for team if folks have any questions on the technology itself before we jump into specific elements.
Anybody has any questions? Perhaps can unmute yourself and ask a question to Srinivas. Maybe Srinivas, just a little bit more enlightenment on this topic, right? You mentioned a few industries, and I saw one of the industries that, you know, highly dependent, or you can see growth is medical and aerospace, followed by automotive. So from your experience, these specific technologies like what we are seeing now on DED, those are used, what kind of areas being used in medical, for example?
So medical would be what I said, right? EBM is one of the modalities that is heavily used for medical technologies. It can create custom design. It has the right porosity capability to use for implants. So this is commonly used. High temperature metal alloys using DMLM, right?
Yeah.
So if you're thinking aerospace parts, in some case, you'd see low volume production being made with DMLM, like the Bugatti Caliber that we talked about. And then high volume production is primarily through binder jet, which is now being matured as a technology itself.
Also for the medical industry.
Medical is not. Binder jetting hasn't seen the application yet.
Maybe, so binder jetting is in
automotive.
Automotive. Okay.
Yep.
Okay.
Good question,
anyone?
Lina.
Yeah.
Yep.
Anyone has any feedback on this? Okay, maybe it's still in the process of absorbing. Yeah, you can go on. And
Sure.
Before you proceed, Srinivas, I would like to apologize. I need to take a leave. I've informed Rita earlier. It's
Sure.
9:10 here. I need to make a move, and I'll catch up with the recordings later. So once again, thank you so much, and have a good sessions.
Thank you, Lina.
All right. Okay, Rita, you can take over. Thank you very much.
Thanks, Lina.
So thinking about process, then the M, the material part, right? In this case, the size does matter. So what I mean by that, as I highlighted, this is using metal powders. The toxicity, I think the community here on the call understands. The risk will depend on the type of metal alloy you're working with. Rarely do we see applications that are pure metal with a single element. It's cobalt, chrome, inconel, stainless steel in different versions, aluminum, magnesium, silicon. They're all applications that exist. But I wanted to highlight why size. As specifically coming out of US, there's been quite a bit of emphasis on combustible dust risk management. Metal alloy powders are a good example where when it comes to metal additive manufacturing, the size of the material has a significant impact in its combustible dust property. What you're seeing here on the table, 15 to 45 micron, is the more common size fraction that is actually used for metal powder printing using DMLM technique. This is by definition and testing a flammable solid of class ST1, so you're thinking sugar, but with a significantly low minimum ignition energy, right? 4 to 5. Now, below 25, you're talking about risk differentiation when it comes to static ignition risk, right? So this ends up in an envelope where you have to think about the class 2, div 1, div 2 design that ensures the right level of mitigation and control being in place. However, you take the same material and you're talking about the size cut point of 45 to 106. Now, this is the D10 and D90 for the particle size distribution. That material is commonly used for electron beam, which is in medical spaces for making implants. Now, as you can see, this is not classified as a flammable solid. And when it comes to minimum ignition energy, it has significantly high value, right? So greater than 1,000. So from a static risk standpoint, this does not present the same risk profile. Knowing this is a key determinant when you think about the implications on how you both store the material, the type of ancillary process that are required, and the space design that has to be in place to mitigate that, depending on the technology and the material you're working with. So knowing this, as you can imagine from an SDS, sometimes it's, I'll be honest, a guesswork, but the good vendors are actually providing that information in section 2 and 11 of your SDS, which allows you to understand what the KST, MIE, and maybe you also need to understand what your minimum explosive concentration needs to be. But if not, my recommendation would be is actually secure that information from your supplier upstream or get the data tested so you have the basis for decision making and risk management framework. It opens the conversation when you have combustible versus non-combustible. Now, NFPA 652 specifically for metal would be 484, govern risk-based design. Prescriptive can be quite challenging when it comes to execution when you are talking about installing an existing facility. But risk-based design allows you and gives you some freedom in doing the dust hazard analysis, ensuring the controls are captured, and move forward with it. Now, it's an expectation in US and other countries are adopting it, something you need to keep in mind. And I talked about the distribution piece. A point to highlight here, when we think powders, size aside and the impact on the combustible dust risk, the very technology aspect, if you can think about depositing powders, the smaller the powder, the lighter it gets. And if you think about a box where you are applying powder layer by layer, staying suspended in the build space is not necessarily conducive for the technology to do its job. So what I mean by that, lighter powders actually start negatively impacting with the optics, which generates the print pattern. So they are made spherically of the right size to ensure they can actually settle, stay put. So the smaller size fractions are taken out by design to make sure you are getting the optimal product particle size distribution. So not necessarily by design by any stretch in the nano space, which there's quite a bit of conversation and early concerns as the business was coming forward and we are building this out. Is like, do we understand that piece? However, there is welding happening, and touch upon in the OH segment, what does it create and how does that impact the risk profile for the material? The last piece, as we kind of think about printers, I talked about the build phase, and this is an example of a sample workflow. There are a couple of key steps, both pre and post, that we need to be mindful of to understand the technology implications. And this kind of highlights this for a laser powder bed fusion system. When you think about the printer for, in this case, the powder bed fusion DMLM system, powder loading in the smaller format system is still by hand. You may be getting containers that are yay big that you are transferring, bringing them inside and pouring it out. I had seen early on the practice of scooping and filling in the build volume chambers, and the larger format systems are actually now self-conveying. So powder loading, depending how it's done, a powder goes in, can have occupational health hygiene issues. The build phase itself, where you're supplying energy and either you're keeping inert gas and vacuum, is relatively benign from a risk management perspective. The units are actually tested for radiation, right? The RCAM system, because they have to be CE certified before they are supplied to the customer. But then when you think about the part as it is being removed, coming out of the machine, there is a depowdering step to some degree that you do, but the build plate is quite heavy, which is typically a metal plate on which the part is actually, I guess, adhered or built in space. So removing that part requires you, depending on the large format printer that I showed about, actually requires crane to lift out the build plate and bringing to the right post-processing step and depowdering. Now, this is one place where I've seen risk not being completely being visible, or people making, I'd say, depending the cost and the implication around it, choices that don't lend itself to good risk management practices. So specifically, if you are depowdering and you're not doing that in a classified system, right? So which is electrically in the right classification, you increase the risk. Many of these applications use compressed air. So using a blast cabinet may not be your best option, thinking around classified systems that can actually mitigate that risk. The post-processing step after the powder is removed, right, may require you to remove your supports and then do some final finishing activity. Depending how it's done in your industry, this may be something that is classically managed. A part that is needed as we think about the powder that comes off, it is one of the materials that's a high value raw material input to the process. It's typically sieved 3 to 4 to 7 times to make sure you can continue reusing the powder as you add virgin powder to it, right? So it's a combination of, and that's sieving in the R&D space when I first saw was actually hand sieving, because they were trying to do small scale work. In industry, there are actually now enclosed systems, not fully closed loop, but you do add the powder in a bin. It goes through a vibrator sieve, could be inerted, could be in this some cases not, and then you get the powder out. But this is one place where you have potential for a metal powder exposure. And last but not least, the first 5 boxes talk to routine, the non-routine elements. Here, the fumes that I highlighted actually get captured in an onboard HEPA filtration system that captures the gas stream. The fume condenses out before it recycled in. That needs to get maintained and managed. You may be doing a material changeout that may warrant cleaning the entire build chamber or any other routine maintenance that you may have to do, which has presence opportunity for creating exposures to powder, potentially in case of maintenance of filter systems, because these are finer powders, specifically like a material like aluminum, you can have creation of flammable gas because the disposal requires you to do it in a wet environment system. And the liquid waste that you may be seeing that can now has to be managed as a hazardous waste, knowing it has metal powders in them that may be reactive or non-reactive in nature, right? So looking across the spectrum of risk, both from not just hygiene, but from an EHS perspective, and having to think through that allows us as professionals to manage and recommend the right controls when it comes to adopting this technology. As I highlighted, a couple of those process implications was touching upon some requirements that flow down in terms of infrastructure or building needs. So if you're thinking about flammable solid storage, now building codes and fire codes have typically a maximum allowable quantity, the MAQ limits, right? So you cannot put a large format printer in a strip mall and be able to say, yeah, hey, look, we can go ahead and do this because we could acquire the space. There'll be a fire protection limits that you cannot adhere to. So thinking about those implications as you bring this in. Fire protection, if you're working with materials like aluminum, right? It's not uncommon for the insurance agencies that your organization be working with to say, look, we need sprinklers because it manages property loss. But this necessarily is not your friend when it comes to mitigating fire risk from metal additive manufacturing. Now, NFPA calls for it. There are solutions I'll touch upon that actually provide suitable protection from in absence of water. What could that be? But that's a part of learning that we had to go through and help educate and partner with our peers to help inform the decision making. Now, powder handling I touched upon from a classification perspective. On the dimension to keep in mind, if you are thinking about local exhaust controls for dust mitigation, common occupational hygiene, engineering control, if it is conveying the dust, is that system classified? And that could also be from a housekeeping perspective if you're thinking about vacuum cleaners. Unique to EBM, because it does use an electron beam, having the right physical clearance, that's the space between these systems, is a key part to ensure the beam's focus and the precision is maintained. And that could be significant when it comes to electron beam based on the size. And then as you heard me talk about the size and the weight, loading and moving parts between these units can be a significant ergonomic risk, right? So how do we think about material movement through our workshop or the industrial facility is a key part to ensure you have the right solutions to enable and minimize injury risk. Now, temperature relative humidity can be an implication based on the material that you're working with, how hygroscopic or what the quality team may need. That may also want you to keep that consideration in mind. So a couple of showstoppers that I could see here that I've highlighted that can really, during your assessment phase, you want to be thinking ahead and informing your facility engineering management teams on this topic. So when you consolidated those points, right? So this is one chart that kind of summarizes this. And I won't read through all of those elements. Few things that upstream you got to know is primarily on the safety side, understand your material, combustible dust nature of it. Keep in mind the fire protection obligations that come with it. Making sure you're also thinking about the ergonomic aspects of doing this work, especially when you think about full rate production and how parts get moved around. From a hygiene perspective, toxicity is driven by the metal alloy composition. A piece that may be for EBM, primarily in US, because these are actually required to be registered in multiple jurisdictions within US. So if you are using this technology, they have to be registered. So that's one part from a license and registration standpoint. You have to keep an eye out, knowing these are ionizing generation units, right? So that's something that you got to keep in mind. Last but not least, on the environment side, if depending on the scale of the work, it may be where if you are doing full scale production, hazardous air pollutants and the local agency may require some controls around it. A key determinant is on the waste management aspect of it, knowing you're working with both potentially flammable waste end stream, and if reuse or recycling of metal powder, how do you want to think about those elements? So that I would say would be the couple of key points to keep in mind when it comes to EHS risk presented by metal additive manufacturing. Now that we have talked about different risks, I'd just like to peel the onion quickly on exposure management specifically for our group. Just want to highlight when we think about controls, right? The framework that IOHA talks about. When you are thinking about risk, percents of OEL are a good way for you to think about risk management practices. And keep that in mind as we think about specific data points. I highlight some from the literature, some from the studies that I've seen that have been published in my prior work. So specific to metal additive manufacturing, this is something I saw in my work in collaboration with NIOSH when I was with GE. And then, as you can see, more and more published literature has come out in this space. When it comes to laser bed powder bed fusion, right, which is DMLM and EBM technologies, you are seeing quite a bit of publication that talks to studies being done in Sweden, in Italy, in US, where there is routine work that results in exceedance of personal exposures exceeding the TLV by significant amount, right? The more recent study done by Bao et al. For direct energy deposition, it was actually a Inconel alloy. They also saw exceedances when it comes to usage of nickel. Now, we all understand the sensitization risk with cobalt. We understand the risk profile. A fascinating study that was early on done by Graf in 2016, knowing the metal powder is fine in nature, they did see particle size, not particle size, the particle concentration difference between ceiling and floor. Now, I wasn't able to recreate in some of the assessments I had done in my work, but this kind of also gives you an understanding when it comes to floor, you're seeing higher values. Now, there's potential for that from a settling perspective, which means when you think about housekeeping obligations, when it comes to material risk and transfer, something for us to keep in mind, right? How do we get good at it? And that also enables reducing your combustible dust risk within your facility, right? So both a hygiene and combustible dust risk that was highlighted. But this was key when you think about the weight of evidence and the literature talks to exceeding from an exposure perspective. We talked about sizes. Raw material inputs 15 to 45 on the smaller size can go up to in hundreds of micron to enable the technology and for the part to be formed. The chart on the left actually talks to some of the work that was done in collaboration with NIOSH, where they did particle mass concentration across multiple size fraction. What you see here is with the EOS M20 machines, employee, when they were adding powders, I talked about hand charging. At that point, that was the way to do it. And then where they were sieving powder, you see spikes. But this is primarily in the 10 plus micron size range, right? So the larger mass contribution was coming from larger particles. Some of the work as I left the organization, and now there is more published work that talks to what happens to that powder as it goes through and gets reused. Beautiful SEM images where you have spherical particles that are being made. The virgin powder is devoid of what you see on the SEM image on the right. They are more larger in size with not as much of these small satellites connected to it. But as you start reusing the powder, once it goes through the gas phase, the welding fumes that come off of it, the smaller fumes tend to agglomerate on the primary powder, right, which creates these nano satellites, right? They're adhered to the surface because for any nano material, if you work with it, it takes quite a bit of processing to make sure they are dispersed fully. So in this case, we knew our fumes side was the reactive, which was getting collected on filters, but it's addition of materials which are effectively of the same alloy composition that adhere to it and create these satellites. That was one piece that helped me kind of think through why that increase in reactivity happens as you collect these fumes. But they don't necessarily transform or tend to be in the nano regime. They are actually agglomerated onto the primary particle and then end up creating these particle sizes. So this was insightful. This was good work, I believe, coming out of Italy that was highlighted in IOHA in 2021 that gives you understanding of how the material changes. It's not uncommon to have material sieved up to 6 to 7 times before it's disposed of, right? So being mindful of that from a risk standpoint is a key implication. The part that we never got in, I wanted to highlight, right? And when it comes to data, a lot of what we do is on the upstream side of evaluating exposures, managing that. When you think about this, is like, hey, look, we do actually have that risk profile. Part I never stepped into, but this is phenomenal work that was done coming out of Sweden, where part of the study was actually looking at biological monitoring. So this is urinalysis when AM operators in comparison to controls and welders. This is a good study that I recommend folks getting a copy of. They did 2 years of data collection early on where the understanding of risk was limited in year 1. You see metal concentration profile at the end of the 1 week study were higher in value across all the metals that they studied. Welders were having similar challenges, actually significantly higher because they weren't wearing the, I wouldn't say required PPE, but any kind of personal protective equipment. The ventilation system design doesn't seem to be robust, where you're seeing increase in the body burden for different metals. As the team that was doing the study worked with the organization and controls, which included both administrative and PPE controls, were implemented. This was insightful to see that the end of shift values for urinalysis were actually lower for the most part, which the authors talked to effectiveness of the controls that were in place, right? So from a solution perspective and providing data, I found this helpful where that was not studied or reported in the past. My prior organization, we hadn't done this stuff, but this was one question that was in our mind: are our controls effective? How would we know about it? And then this kind of highlights to usage of what I'd say standard industrial hygiene measures, occupational health risk measures that mitigate the risk in the AM population. And you can also see from a technology perspective, additive versus welding, right? The body burden is significantly higher when it comes to welding if you're not using the right controls compared to AM solutions. So knowing the risk profile, knowing the data, what can we do? I think we're all familiar with the hierarchy of controls. And in the next couple of slides, highlight key user and equipment specific controls that'll kind of give us a good feel for what things we need to be advocating for when you think about adoption of this technology. When it comes to the machine itself, there are inherently designed controls that are important that every vendor is keeping in mind. Knowing these carry combustible dust risk, the loading door is interlocked, so you cannot open when the laser or the EBM system is actually firing. Knowing you're focused on mitigating the combustible dust risk, vacuum or dual oxygen sensors, which ensure the cabinet is, the build envelope is inerted. Did highlight HEPA filtration, which is part of the design to ensure gas emissions from the build chamber are contained and captured. In case of some of the systems, there's actually laser active leak detection, and then the shielding, which is on the viewport, so you're not exposed to the UV radiation. And in cases of large format printers, like you see is an X-line system, the powder feed and the sieving is actually in a closed loop design where the powder is first added to the build chamber here, and that gets pneumatically conveyed and then recirculated back, right? This is becoming I'd say, moving towards the norm of how large scale production needs to look like, right? Minimizing touches to the powder, both from a safety perspective as well as from a product quality perspective. It mitigates both risk, and I see manufacturers and OEM moving towards this. But then there are specific user controls which tend to be presented by OEM as optional. And here's where in my experience, we saw the biggest challenges and where the risk starts creeping in. Depowdering is a good example. Here you see an example of a blast cabinet. Now, this may be acceptable when you're doing it with a non-combustible dust material like an EBM or a material that has a very high minimum ignition energy. But we were working with materials that were flammable solids. And I'd say close to 2019, 2020, where Solicon came up with an explosion-proof depowdering station. Phenomenal solution, definitely capital intensive, but it met the performance needs and the requirements that we had both from a safety and quality perspective. That is becoming more of a industry norm and solutions you can go after. Sieving, powder part movement, those are a couple of things, and I highlighted two examples. Automation is going to be a key way to solve for this problem. General Electric provides you a suite of solutions where you can use, whether it be the powder recovery system, parts being moved, a station that allows you to go from one to PRS to actually sieve it. Or you're talking about Workman, which is another solid user. This is an example of a BMW line we are doing end-to-end using AGVs, automated guided vehicles that you see in Amazon warehousing system that can transport your part, which are quite heavy, take it from the printer, move it to a powder recovery system, and then completely go into the final stages, right? So to get to that final end stage, this is one space where I can see ergonomic risk with full automation being the solution that people are moving towards and industry is moving towards it. But you may have to ensure that as you think about adoption, you don't lose sight of things like these trolleys and the PRS system that allow you to mitigate risk. A piece that may be needed based on the material type is dedicated powder handling rooms, which is one approach to consolidating your both occupational health and combustible dust risk in one space. So specifically focused on sieving. We were doing our depowdering in the dedicated space that was designed for it, and it enabled the right level of robust controls being applied to one space versus the entire facility. Right, so that was one thing that we had to, in our new greenfield construction, be mindful about. And then you have your couple of key other controls that I wanted to highlight when it comes to fire protection. Grounding and bonding, one piece that there is actually a OSHA citation for is prevent use of unclassified vacuum cleaners. So it was a requirement to have an 8X class 2 vacuum cleaners required, whether it be a wet or dry system. I did highlight water not being a friend. Class D fire extinguishers are relevant for metals, but one which we found helpful in our large powder production facility was an F500 encapsulating foam. This is specifically capable of quickly reducing the temperatures of the fire and isolating and preventing oxygen from getting in, which upon dispensing reduces the fire potential for that. This was in large-scale power production systems that we had up in Montreal. That was one application that we were trying to get field tested to make sure the deployment can be done at scale in our other facilities. And last but not least, when you're thinking combustible dust, I've highlighted both from an occupational and combustible dust risk is housekeeping, right? So keeping those key things in mind, right, is a key element when you think about deployment. With admin controls, key probably closer to this group would be around MOC and chemical approval program, making sure we understand the property of materials coming in, making sure you are doing routine PP and housekeeping audits as part of your 5S program to ensure it's both clean and the PP is effectively being used. I'm sure from an occupational hygiene, depending on where you guys stand, monitoring of these with aerosol monitors is a great way to kind of get a feel for which tasks present the risk and think about educating that when it comes to operator usage of PPE. And last but not least, an effective element of our risk management part is PPE. So flame retardant coveralls were required in the large powder production facility. We also required that of our operators when they were working and performing maintenance tasks. This was important. If operators If they're not doing maintenance, it was FR lab codes, right? So that ensured any kind of, in case of a fire risk, we had the right protective gear. ESD shoes and respirators, depending on the application and the task that was being performed. PAPRs were definitely preferred, especially during the larger powder removal phase, and then doing both sieving and maintenance activities, just from a comfort perspective. So those would be, I'd say, highlighted solutions. So when we think about the key lessons learned in case of metals, for infrastructure, it's ensuring that you understand your building classification, think about your fire, both fire rating for the building and the sprinkler, and having that active conversation upstream as you think about technology being brought in, because as we know, it becomes quite expensive to retrofit a building with the right requirements. With material, the characteristic of whether it's flammable, water reactive, ensuring you have the right data to have the right conversation. And a key part when it comes to metal powders, right? They are in micron size, not nano. So the risk profile, even though you have nano satellites which are adhered to it, you do have to think about the reactivity of the material that you're working with and manage that effectively. And from a process perspective, I cannot emphasize enough that you think about the ergonomic solutions, that they are implementing it, ensuring you have the right 5S work practices to mitigate both combustible and exposure risk. And lastly, but not least, ensuring you use explosion-proof HEPA vacuum cleaners for metal powder handling, right? So a couple of key takeaways on the metal powder side. I'd want to pause, do a quick time check, and then open the floor for any questions. I do see some.
Yes, we've got 2 questions in the chat box.
So Bina has, what are the touch points for major human processing closed? So here's where I'd say, Bina, right? So this slide talks to it. The printer in itself during powder loading and then part unloading has human touch points. The build phase is completely enclosed, but you're also doing sieving and maintenance activity that requires human interaction. Now, if you think of the fully automated stuff, which is in large scale production and an organization never gets to, will take time to mature to that end state. So a lot of that typically tends to be manual with human labor being involved. But if you go down the automated route, you may minimize those exposure steps. Where you cannot get away with it is maintenance activity. This very much requires human interaction. Is it possible? So hopefully that answers your question when it comes to metal powders and then both DMLM and the technology portfolio. Is it possible to obtain health statistical data on specific exposure of the worker? So published studies that I've highlighted have their respective data points. You see a couple of the key author names that are listed out here. So I think that would be the extent that I'm understanding your question is referring to. If not, Denise, if you can maybe expand on your question, maybe if I didn't get the question correct, I may be able to answer that when you say statistical data.
Taylor, does this answer your question?
Now it's clear. I mean, it depends on the metal or other materials. I mean, I ask TLV, TVA. So it depends on the activity and on what is the specific material you use.
Yep. No, fair point. If I'm hearing and understanding what you said, right? So the studies refer to the raw materials they work with, right? So it could be Inconel, which has nickel and cobalt. So this is just the literature.
I mean, it's not a question of toxicity of nature of powder, but a question of how the worker do it. Do you understand what I mean? In which context Is an exposure question, not a toxicity question.
Sure. So these are full shift samples.
So I say
right?
health data, statistical health data. So it's something about the process, the specific process. And so if it's metal, it's metal. If it's plastic, it's plastic. It's different process. And so different risk. Do you understand?
I think I do. So if I've heard you correctly, let's see if I captured your thought here, right? So material toxicity is function of raw material you work with. Fair enough. The exposure touch points that you have. Now these were full shift exposures that were captured, so time weighted average. So for an 8-hour sample, and the authors that have I'm summarizing the data here actually does statistical analysis to kind of talk about the mean and medians and what the exposure ranges were, right? So I kind of looked at that as a gauge for, are you seeing consistent over exposures, or in what spectrum, if you just think about exposure bands that you're looking at.
Yeah.
My personal experience, we had specific tasks that presented higher risk. So I've highlighted when you're doing depowdering step, that was one that presented challenge. Sieving and maintenance, those specific tasks were quite challenging for us to control for early on. As we matured, we are able to refine the process, put controls in to make it better, right? So thematically, the trends towards over exceedance is one that you see. Not that it cannot be managed, but you have to be mindful of it.
Oh yes. So I mean, it's 50% in certainty, or if I have a worker in Italy and I want to make a comparison, I use this threshold plus 50% of other less than 50%. If I want to have a initial provision.
Yeah, so you're talking, if I'm hearing you, maybe the action limit, right? So
Yeah.
I encourage folks to, this is where and it's one established, and maybe the regulatory regime calls for different. Action limits are a very common way for you to think about implementing risk mitigation controls. What I encourage folks to think about is not just the action limit. Where do we feel there is good, robust statistical evidence that we have managed the exposures well, right? At 50%, you're still having the probability that you may have exceedance risk, depending on how many data points you have. So a target would be, can you bring it down to less than 10%, right? So in this case, we do see quite a few data sets that talk to exposures exceeding 100%. Right. So focusing on those tasks with real-time aerosol monitors would be a great way to isolate tasks, and then you can focus your exposure mitigation on that specific step.
Oh, is all right. Thank you.
Yep. Other thoughts or questions before we jump into polymers? And maybe Rita, quick time check. We got 30 minutes.
Yes, perfect.
Okay. Questions from others before we jump into polymers? All right, sounds good. We'll just roll into it. So polymers, now there is a wealth of evidence in this space, knowing the capital cost, much easier to acquire, definitely one which went through its own Gartner hype cycle early on than metal additive manufacturing, which is kind of feeling the same challenge, trying to get up from the trough and say, hey, can we scale and make parts? So there is quite a bit of literature and concern that came off, primarily being driven from exposure chamber studies, and we'll touch upon some of this data. The three key processes, right? So again, IMP, process type is material extrusion, which is the small format FDM printers that you're seeing. Material jetting, which is like, again, a version of I say screen printing, and then VAT photopolymerization that we'll touch upon. So on the process side, material extrusion, in this case, it's a solid pipe filament that is actually heated through a nozzle, and the plate actually moves in an X, Y, and Z envelope, where it's the heated filament is actually deposited in the 3D pattern. Common materials that have been studied quite a bit is ABS, acrylobutadiene styrene, polylactic acid, but some of the new materials are polycarbonate and Ultem. You've seen the small format printers, but if you're working with larger systems, they may even use materials like Kevlar or things that may be also containing embedded nanomaterials. I did not see that in industry applications, but there may be some unique application spaces that may be the case. One of the common needs for something like this, because you're creating a material, it also has support structures like metal, which then needs to be removed. So it's not uncommon to have a small weight % of caustic material being used to remove the support material, which ends up making the final net shape product that you can easily handle. Right, so that's a common piece for material extrusion technology. And I highlighted the use of need for continuous fiber, Kevlar fiberglass being some of them. Material jetting on the other part, so this is more on the smaller consumer application space. When I think industrial is both material jetting and VAT polymerization. This is actually designed well from an industrial use perspective. Two-part material, one is a photopolymer and wax typically, which is provided you in two distinct darker colored jars. Think of milk jugs that get dispensed right into the system. You just place it, the system connects, and then the material is actually dispensed from a printer head. They call it a jetting head, which is sprayed on the application process on the build plate. Very similar to when you think about how it works to binder jetting, but you don't have the powder plate at the bottom on which the binder is placed. As the material comes out, the layer itself creates the part in which is subsequently cured with UV light. All of this in an industrial system has the controls. It's completely enclosed system. What we did observe for material jetting, early on, there were no active exhaust systems in place, right? So they vented in the room, which was a challenge from an implementation and a risk perspective when it comes to volatile organic compounds or VOCs. As the part gets made, because it has both the photopolymer or wax, UV lights cures the polymer part. The excess wax need to be then removed. So part is then either heated in an oven or submerged in molten wax to remove the excess wax connected to the part. As you can imagine, you are pushing the photopolymer through the print head. It is quite common that as you go through build, or depending on the build quality, that you may be using acetone for cleaning the polymer and then isopropyl alcohol for removing the wax and creating the net shape. So two common solvents that are seen quite a bit of application is a common use. You may see a IPA bath in which they may do it, or an acetone to end up cleaning it. So how do you keep it close, making sure it's not evaporating, right? So common industrial hygiene techniques that can mitigate that risk. A common need that we saw was also need of climate control environment from a product quality for both material jetting as well as for VAT photopolymerization, which is the next industrial technique. So VAT polymerization, one of the larger primary cool application spaces I see. I highlighted the 3D printed shoe by Additive and a couple other manufacturing where the sole is designed. In this case, the energy source is actually sent through the collimator. It goes onto where the entire vat or a container is filled with photopolymer resin. It does not have the wax, but you effectively pour it in. Definitely creates an odor, right? So from a indoor air quality or environmental quality issue, odor concerns are quite common with both technology, more so for VAT polymerization. The solid state laser is used to cure each layer as the build plate descends. So there's a fine layer as it comes down, which that can cure the plate comes down, and it keeps repeating the process. Post-processing in this case is again caustic, and the part itself has a final cure step, which is put in a UV box to fully harden, enclosed, not necessarily from a risk standpoint, a high-risk task. And need for climate control is key because you're working with open batch systems. We did some initial monitoring both indoor and outside. The SDS, which I'll touch upon, kind of talks to what the exposure risk would be. In this case, SDS material, as I talk about, right, knowing your material, actually has common ones that we saw had epoxy, acrylates, which were known as both dermal and skin sensitizers. But if you can think about the molecular nature of the materials that are highlighted here, they're high molecular weight compounds, right? So higher the molecular weight, they tend to be non-volatile at room temperature. Neither of these processes are heated process, so you're not driving off VOCs. They are at climate control environment to get good product quality. But the thing that you need to be aware of, which many of us know, acrylates and epoxies are sensitizers in nature. So how do you think about the right PPE controls and making sure whether it be glove usage is more diligent as they are both handling the raw material and the cured product. Cured product typically does not have the similar risk profile. Antimony in this case is something we saw in smaller quantities, and an example of an SDS that's something that doesn't, from an exposure risk perspective, was present in any of the sampling studies that were done in my prior role. Knowing this, one, you may be wondering, so I kind of touched upon the liquid side of it, but one that warrants, and if you are adopting this technology, you're thinking about, well, I'm sure what is in the FDM, the fused deposition fume, right? So it's the heated filament. And work that was done by IOHA Davis in 2017 replicates and really does a good job of showing you of the distribution of materials in the fumes that may be coming off. Just from SDS, styrene, formaldehyde are two common examples. Acrylates and acetaldehyde are one you can see across the different material types that you're working with. Things like aldehydes are known to be carcinogenic, having to be mindful of it. Acrylates are sensitizers. The key part that, if you think on the material chemistry side, heated, how much of the fume comes off, what does it mean from a risk standpoint? And there was quite a bit of excitement in the early part of literature, which talked to, hey, we are able to measure the particle concentration that was coming off. Nano was big, almost 5 to 7 years back. There was quite a bit of measurement technology that was out there. But the question that I was trying to answer from an implementation standpoint, are these fumes presenting health risk? You are seeing particle counts because you can measure for it, but what does it translate from an IOHA exposure risk management standpoint? So wanted to highlight one. I used to have a table in my prior slides, which I had to pull together. Stepaniak from NIOSH has done a phenomenal job in his 2021 publication in Journal of Toxicology and Environment Health, which talks to exposure to both gas and particulate emissions from multiple technology types leading all the way up to 2020. And this is just one of the tables, just to give you a feel for it. I didn't capture, like, I think he's got 10 tables in there that talk to the different exposure profiles. A lot of the studies talked about measuring for acetaldehyde. You're looking at formaldehyde. You're looking at styrene. These are all being measured in microgram per cubic meter, which is the airborne concentration that were measured in work environments. Now, to anchor this, right, these are not in milligram, but in microgram. When you convert this into ppm, many of these values, right, were exposures that were less than 5% of the lowest occupational exposure limit. Typically TLV driven, but if you're looking at your country specific numbers that talk to truly from an exposure perspective, these were really low risk emissions, when what I would call probably in a well-controlled state, right, coming off of the systems. However, there was quite a bit of excitement, and that continues to be, with emission studies and understanding how these particles, which is the particulate phase, how are they different or unique? And the study by Rodney and Weber, which was done at the 3D Printing Summit in 2017, actually summarizes that in a very effective way, kind of talks to particle emission rate during printing of a standard part. And if you can look across using multiple materials and a good sample size, they compared the average emission rate during print with 3D printing material PLA ABS compared to laser printers. And you can see the emission rate is no distinct or different. And one could argue, for the most part, lower than what you see from laser printers, right? So these are large format, small format printers that are everywhere in your office, perhaps even at your home. And the maximum number concentration, very similar in range when it comes to actually lower, I guess, compared to laser printers. And similar to what we saw in our health hazard evaluation that was done by IOHA, right? So we had around 10 to the power 5 particles per centimeter cube. So when you think about emission rates as a determinant, if you're thinking about it, real question comes down to, are they any unique or different than what we see in what we'd call other types of printers that are commonly used? Many of these were actually done in exposure chambers. So you are putting a printer in place, enclosing the envelope and capturing the emissions coming off. So really your worst case scenario. But when you think about implemented in a work environment, the studies that were done capturing specifically the gas phase does not talk to, when you think occupational risk, a well-controlled scenario from a exposure risk perspective. Piece that I think this is a study done by Liso et al. Published in 21. And maybe as you hear me describe this, quite a few good studies have come out in the last few years.
No, stavo seguendo un webinar, vabbè, ma tanto è.
I think somebody went on mute. Perfect. That talks to, yes, we understand particles are emitted, no different than lasers. That was helpful with peer-reviewed publication. The exposure profile is low, but what does it mean from a toxicity perspective? So 2018 study, now I've highlighted a couple as a snapshot. It talks to actually the one by Gumperlin, and I may be butchering the author's name. They actually subjected 26 healthy volunteers in an emission chamber, which was generating polylactic acid fumes and ABS fumes over a period of 1 hour. When they exposed this and they studied their both nasal and urinary biomarkers after 1 hour of exposure, so it's a short duration exposure, right? They did not see any significant differences pre and post exposure in the biomarkers. Exhaled nitric oxide was somewhat increased after the ABS exposure. So this was a unique example, which I find fascinating, where they actually were able to test emission chamber studies with healthy human volunteers and be able to evaluate it. However, work that has been done prior to that talks about symptomatic increase that was witnessed in, I'd say, what is common use environments, whether it be educational institution or you may be doing with smaller systems. So symptomatic response, yes, but definitely no significant difference in biomarkers. If you use this data and you compare and contrast to either cellular studies or animal studies, the reactive oxygen stress, ROS, and then when you talk about inflammatory markers, in cellular animal studies, they are showing that they are significantly higher, but you don't see the similar response in human health studies. By no stretch, I'm a toxicologist, but that was insightful for me to kind of see how the data across species is different, both at the biomarker level. That gives us both an indication of where we think around risk control and how we can mitigate this when it comes to additive manufacturing. So a couple of key considerations when I kind of summarize this. Sensitization risk exists, knowing the nature of polymers that you're working with. Now, VOC and nuisance odors, that is one that we were focused on, knowing we all want to have both a safe and a pleasant environment to work in. How do we think about that and mitigating that upstream? The systems are enclosed and designed at class 1, so from a risk perspective, not as much when it comes to non-ionizing part. One we saw early on during adoption was quite a bit of hand lacerations, right? So post-processing, using of sharp tools, we would get hand cuts because they would be scraping a part out of the build plate. So moving towards something more robust, or using techniques of securing your build plate, not keeping your other hand in place as you remove parts, but some common solutions that help reduce our injury risk at this point. And from an emissions perspective, the key challenges where I think risk starts to get higher is if you are talking about large scale format with multiple printers, right? How do you think about your waste management? So far from an environmental regulation perspective, the VOC emission from industrialized systems are not much that warrants us any emission controls in US. But that's something that we were always mindful of and keeping ourselves in check when we think about environmental risk. So what are some controls similar to metals? Few that are equipment specific, right? So loading door and UV systems are interlocked. For polymer jet or material jet, it's the canister style system, so it reduces thermal exposure. The vendors are thinking about it. But then few that I think are worth thinking about, especially for large scale printing, is user specific controls. Your 1, 2, 3 printers in a large office, not an issue. But we had a bank of 25 printers. They came, as you can see on the object on right, just I'd say no better than a MERV 10 filter system that was part of the printer, and that would just went right in. You could smell the odors. We knew over time as it is, there would be concerns. So we actually designed and installed our own ventilation duct, which was connected to a singular system that passively captured the fumes and then discharged it outside, right? So the positive pressure from the system was enough to carry it and take it out. So not a significant investment. Here's an example of how BMW is doing when it comes to their deployment with printers. They have designed and installed a duct system to just take away the fumes. NIOSH did a study in 2019, and they did with what I recall like 20 plus systems. And one of the recommendations was if you are doing large scale, even consumer style printing, like in a makerspace, installing these are one easy way to mitigate the indoor air quality issues that you may be thinking about, right? So think number of systems and then start thinking about potentially ventilation controls that mitigate that risk. When it comes to the thermal exposure and use of solvents, nothing unique and exciting. Use of disposable nitrile gloves were quite effective. And we use butyl gloves when we're doing cleaning because the immersion and the contact time is higher. A key part I do want to highlight, because the implementation of these systems are done by a vendor, right? Thinking on the control strategy upstream, depending on how you're doing it, can impact your project scheduling timeline. So having that clarity, making sure you're advocating for these controls specifically early on will help minimize any scheduling impact from a EHS team and from a controls perspective, right? So those are a few things that you want to keep in mind. So key lessons from my standpoint, all right, and I think literature points to it and kind of validates some of my early experiences. The VOC concentrations that we see are significantly below established OELs. The excitement around ultrafine particulate emissions that we can measure for, very similar to laser printer emissions, right? So when we think about, hey, what does that mean? Do keep both of those parameters in mind when it comes to talking about this risk to your stakeholders. What I would recommend if you're scaling up the number of printers, not just think indoor air quality, I think it'll be prudent to actually provide local exhaust to mitigate that risk. And the part that is around photopolymer usage, sensitization, the gloves and the cleaning agents, it's something that we can absolutely manage. And do think about hand laceration. It's one I saw quite a few of, and we reacted to it, but it's one we can anticipate and put some good controls in place. So that kind of summarizes, I'd say, key takeaways from polymers. I'd pause here, perhaps take questions from the team, and maybe just wrap it up with 1 or 2 slides on standards and where we are headed. So questions from the group. I believe we have to line 15.
Are there any questions from our participants?
Hey, Srinivas, it's Michael Rosenow from Los Alamos National Laboratory. How are you?
Good, Michael. Thanks for joining.
You bet. Great job this morning. Hey, I've been out of the 3D space for quite a while, but back in the day, I recall that single wall, the multi-walled carbon nanotubes is an additive on some of the polymers was a concern. Is that still looked at strongly, and what have you seen on that in your research?
Yeah, so from an industrial use space, early on, people were saying, hey, that could be one of those special application spaces, right? Depending on what you're trying to work towards. So I'd say maybe a very narrow use case than a ubiquitous large scale use case. But something you got to be mindful of, especially when it comes to FDM, that it may be there, but we didn't see a whole lot of that. And from a risk standpoint, yes, so emissions of the material, I think there were some studies that were done early on by NIOSH, again, focusing on particulate emissions from FDM, right, that I highlighted, where the emission rates are similar. With that material property, I think there'll be prudence in capturing that emission versus having a printer just as exhaust in the open work environment, right? We know the Michael, does that answer your question?
Yes, thanks a lot.
Mm-hmm. Question from others.
We still have 5 minutes left in this meeting. If there's anybody that's got a question, you're welcome to raise your hand or put it in the chat box. We've got a comment in the chat box. Thanks for the comprehensive presentation. I guess that exposure assessment studies were based on offline measurements and comparison with 8-hour limit values. What about short-term exposures?
Andrea, is this referring to polymers, metals, just to make sure I can anchor?
The question is about emissions from polymers. For instance, formaldehyde. I was wondering if short-term peaks can be assumed and might possibly have health impacts on workers.
It's a good question. So the summaries that I personally went through, and then what's been presented by Alex Stefaniak from NIOSH, were time-weighted averages for full shoot exposures, right? That's what I saw as data points. I don't recall specific short-term exposures for formaldehyde. So couldn't comment. Typically, the profile for emissions, if you're looking just from a particulate standpoint, you would see during the build phase, the values from particle counts climb. So gas phase, I'd expect to be higher than it comes down. But I don't know or I don't believe as the print job is going, there is episodic increase, right? You would see a gradual increase in your concentration, specifically if you're in an unventilated space. A single printer running FDM, I don't see that as an issue.
Thank you.
Yep. And 50% OEL is a good threshold. Well, risk mitigation frameworks are, I'd say, both driven by your organization and sometimes it's jurisdictional specific. So what does the regulation call for? The action limit is a good starting point to keep in mind, right? In case of metals, we had exceedances. You're seeing literature, so do focus on it. When it comes to polymer, the weight of evidence with the several studies that have been done in this space tend to indicate that the exposures are low, right? A validation assessment is always helpful for your own stakeholders. But if I were to say, yeah, which is a higher risk technology from an occupational hygiene risk management standpoint, metals, no doubt. Polymers, manageable unless you have some unique use cases with materials that are not your traditional ABS PLM material that I've highlighted here. Other questions? I'll in interest of time, I'll just keep kind of wrap it up with the next couple of slides. So one of the biggest things that we look for any new technology, right? We have a good feel of what welding means. Metal additive is nothing but sintering or welding in a box, but there are other aspects of exposure profiles you have to keep in mind. But there was a lot of excitement and energy in this space to say, hey, let's kind of go build the framework out, both on the technology, quality standpoint, and safety. As I went back and re-looked at it after being off from 2 years, it was interesting to observe ASTM has completely shut down their scope of work when it comes to EHS standard, and ISO TC261 is primarily one that's focusing on bringing forward some safety specific standards, primarily focusing on material and the requirements for powder bed fusion. So these are the two spaces where there is no final standard, but it's under development. So that's something that you got to keep in mind. UL actually has a published AM facility safety management standard. Paul, I know you are on the call, probably could even comment on it. This is one that came in mind that talks to infrastructure risk. Now, again, not a requirement, but there is an anchoring on what things you must consider, and UL actually certifies your production facility as being AM adherent, if I may call it. There is no compliance comments behind it, but that's something for teams to keep in mind, right? So standards are not coming, anticipate the risk, and deploy the controls that kind of I've talked through in terms of the risk management framework. And one piece, right? So as we think about technology, the way it moves, construction is a big landscape. Just wanted to highlight when it thinks of future of work, right? You're talking about 3D printing, material efficiency, even in construction. In Texas, Austin, they are building out houses up to 300 to give you an initial proof point. So it is one that's going to impact not just industrial manufacturing in the way we see world. And wanted to close with this thought, right? As we think of technology, let's not check out our good EHS hat. It's not always around one dimension of risk, right? Classic example of lotto, if you don't control, you don't close it off. Don't do what I do, right? Don't unplug the oven or just leave your stove on. We may have some additional common risks that we have to be mindful of. So make sure you keep those in mind. And the holistic view is always helpful when it comes to managing this risk moving forward. And if you are thinking about additive, just wanted to highlight completely fully 3D printed shoe if you're thinking for a gift idea for one of your mates or for family or for yourself, right? Something hopefully for holidays you can kind of check out. So Rita, that's all I had. Thank you for the opportunity, guys, for listening in. And for any questions, reach out to me at the email I've listed.
Thanks so much, Srinivas, for joining us today for a very insightful webinar. And from the comments in the chat box, the participants also enjoyed your presentation. So thanks so much.
Appreciate it. And want to wish everybody a great holiday season. This is one we are coming in, so enjoy, relax with your friends and family.
For everyone that joined the webinar today from all over the globe, thanks so much. Go well, and it won't be soon, but we're in the process of publishing our webinars on the IOHA website, so just keep an eye on that. We will be giving codes to our member organizations, and with that code they will be able to access these presentations, but that will only be in the next year. But we thank you, and keep an eye out on following webinars on the IOHA website. And there we've got Maharshi joining.
Hey everyone. Hey, I was conducting another training, so I could not join this morning. But hey, Rita and Lena, thank you for coordinating. And that I just finished that training a little bit earlier so that I can just join with you last few moments. I saw the presentation from Srinivas yesterday as a part of the trial. He has trying to find out. His expertise are very unique in this area. And I had heard about this, and then I thought, let me request him if he can join us and share with us. This is a unique, new, relatively new field compared to what we have been studying on occupational hygiene. So Srinivas, we, all of us at IOHA appreciates very much what you have shared with us today.
No, thank you, Marishi, for the opportunity. Appreciate it.
Right. And see, in addition to expertise in this 3D printing area, Srinivas has been contributing in occupational hygiene in number of other organizations at IOHA, at BGC and other places. So going beyond the work as a part of voluntary contribution also. All right. So
No,
once again,
it's our collective inputs is what makes us better. So I think till the time we continue to collaborate, I think there is no end to how we can improve worker health and safety. So I think that passion, Marishi, that you bring and the team brings. So I appreciate that I get the opportunity to share this with you.
wonderful. So just to let everyone know, there is a one more webinar happening. What is it, Rita, on December 13th, we said, or 12th? 13th.
Yes,
Dr.
13th.
John Mohasan is going to do this webinar. We have a few minutes. Let me not take your time. Are there any questions that you need to answer, Rita? Are there any, or are we ending the session?
No, we on the end, Maharshi.
On the end. So let me share my desktop very quickly with you for the next webinar that we have so that you